In this video, we're going to be talking about the different ways that we can represent double replacement reactions or precipitation reactions. So essentially, there are three different ways that we can represent reactions occurring in solution. The first one is known as the molecular equation. The good news is that this one you already know how to do, because this is kind of our normal chemical reaction that you're already used to writing. So the molecular equation is just kind of a new word for something you already do. The second one is known as either the total ionic or complete ionic equation. And last but certainly not least is the net ionic equation. So one other thing that we're going to be adding in to our equations from now on, whether they're one of these types or not, and you may have done this in Chem 1, but you might not, is that we're going to start representing the state of matter, whether something is a solid, liquid, gas, or dissolved in solution, as part of our chemical equation. So we're going to represent the state of matter of each reactant and product by adding a subscript letter after the formula. So if something is a solid, we put a little s in parentheses after the formula. If something is a liquid, we put an L. Personally, I always do a script letter L, just to avoid confusion with the number 1, but that is totally a personal choice, not a requirement. G for gas. And then the last one that we'll use is AQ for something that is aqueous, meaning that it is dissolved in water. So remember that an aqueous solution is one where water is the solvent. So if we say that something is aqueous, we mean that it is dissolved in an aqueous solution or dissolved in water. So now we can get into these three different types of equations, and the states of matter are important for how we go about writing these different types of equations for the total ionic and for the net ionic. So we're just going to walk through one example for all three of these different types so we can see how we represent the same reaction in three different ways. So the first one, again, the one we already know, is the molecular equation. So this is the one we're used to. One we already know. This is often the easiest to think about, mostly because it's what we're used to, and it's also the most reflective of the lab procedure. If I tell you to go do a particular reaction in the lab, it's going to feel very much like the way you would write a molecular equation, that I combine sodium chloride and calcium nitrate, and I go get those two bottles and I pour some together, like I did in the last video. And so in that way, the molecular equation is useful. However, it's not actually an accurate depiction of what's happening at the molecular level. So we have kind of pros and cons to each of these. Usually this is kind of the easiest to think about, and it's the most reflective of lab procedure, but it's not an accurate depiction of what's going on microscopically. Yep. Remember last time we talked about how when an ionic compound dissolves, the ions split apart. Well, in a molecular equation, they're shown stuck together, even if your stuff is dissolved. So the example that we're going to be working with is the double replacement reaction between sodium chloride and lead 2 nitrate. So if we want to write this out, we'll need to come up with the formulas for our 2 reactants and then swap partners to get our products. So sodium is +1 and chloride is -1, so those will combine in a 1-to-1 ratio. Lead 2, the Roman numeral 2 is telling us the charge. So that is telling us that that is lead with a +2 charge on it. And nitrate is -1. So again, just as kind of reminders here, sodium is +1, chloride is -1, lead is +2, and we know that from the Roman numeral. Nitrate is a polyatomic with a -1 charge. So since lead is +2 and nitrate is -1, we'll need 2 nitrate ions for every 1 lead. So when these undergo a double replacement, our ions swap partners, lead and sodium trade places, and we'll end up with lead combined with chloride, but that lead still has a +2, and chloride is -1, so we need 2 chloride ions for every lead, and then we will have sodium paired with nitrate. Sodium is +1, nitrate is -1, so those will combine in a 1-to-1 ratio. So at this point, we need to balance the reaction. We can see that it is not balanced because we have 2 nitrates on the left and only 1 on the right, 2 chlorides on the right, and only 1 on the left. So to fix that, we just need a 2 in front of sodium chloride and a 2 in front of sodium nitrate. So at this point, the only thing this is missing is the states of matter that we mentioned before. And for now, I'm just going to tell you what they are. You do not currently know how to predict this. You will learn that very soon. But for today, I'm just going to be telling you what the states of matter are so that we can work with that. Learning how to predict this is a lesson for another video. So lead chloride, PbCl2, is the only solid here that is not soluble in water. Everything else is aqueous. So both of our reactants, sodium chloride and lead nitrate, are aqueous, and the sodium nitrate product is aqueous as well. So this is the reaction that we're going to be working with as we move forward to our other types of equations. So the second type of equation that we can write is known as the total or complete ionic equation. So in this type of equation, everything is represented how it actually exists. That sounds a little weird, but it makes sense once you actually flesh it out. So what do I mean by that? This is again coming back to that idea that an ionic compound dissolved in water is separate ions. So in the molecular equation, we showed the ions still attached even when they were aqueous. In a total ionic, aqueous ionic compounds, there we go. Aqueous ionic, no, I was spelling that right, sorry. Aqueous ionic compounds are represented as two separate aqueous ions. Anything else is left together. So all other states of matter are shown as intact compounds, not split apart. So everything else stays normal, but if something is an aqueous ionic compound, it's separated into its different ions because that's how it actually exists. So this type of equation is the most complete molecular level picture of what's going on. It shows you every single thing that's in your container in the state that it actually exists, that, you know, your sodium chloride has separated into sodium ions and chloride ions, so we write them as two separate things. But the drawback here is that they're really long and cumbersome. So they're long to write out. You'll see shortly. These guys can be kind of a pain. What was I saying? Sorry, train of thought, left the station. So they're kind of long to write out and complicated to look at. So in these equations, it can be easy to kind of overlook the useful information because there's just so much information. So coming back to our same example, starting off of our molecular equation. So this is the molecular equation we wrote up above. We have 3 different aqueous species and 1 solid. So the aqueous ones are going to get split apart into cations and anions. So we're going to take this and we're going to split it into 2 separate ions, Na plus and Cl minus. Now, this coefficient of 2 applies to that whole compound. That means we have 2 NaCl. So that means we have 2 Na and 2 Cl. So that coefficient is going to end up applied to both of those in our total ionic. Our next compound, lead nitrate, is also aqueous, so that's going to get split up into its 2 separate ions, lead and nitrate. So we have lead with a +2 charge and nitrate with a -1. Now we have this subscript down here, which is telling us that we have 2 nitrate ions. So the subscript only applies to the nitrate, but it becomes a coefficient in our total ionic equation because those two nitrate ions are separate pieces, that they become separate chunks when that thing breaks apart. A coefficient means that there are two separate, independently moving, not connected to each other particles, which is the case here, that your nitrate ions are not still connected, all of your ions separate. The nitrate, however, stays intact. A polyatomic ion will stay as a polyatomic ion because the nitrogen and the oxygen are actually connected by covalent bonding, which does not break when these dissolve. So moving on to the product side, we have a solid next, PbCl2, which is going to stay exactly as it is. Solids we do not change. So that is just going to move on down. Because in a solid, those ions are actually connected. So we're showing them connected because our goal in the total ionic is to be as accurate as possible. When we get to our last piece here, we're going to have sodium and nitrate, which I made that too big. Sodium and nitrate, which will get separated since this is dissolved in solution. And we once again have a coefficient out in front, which applies to both of our ions. So we'll have Na plus and NO3 minus. Yes. And we will have 2 of each of those thanks to that coefficient. So, what else did I need to say here? One other thing to notice is that I am including charges on all of these ions. So whenever you're writing one ion by itself, not part of a compound, you must include charge. That is a critical part of the notation when it is part of a compound. So in NaCl, the charge is assumed to be there, but it's neutralized by the chloride, so we don't write it. But when sodium is by itself, it has a positive 1 charge, and we need to represent that. Sodium with a positive 1 charge is very, very different than sodium with no charge on it, chemically speaking. So we need to keep track of that. So then our third and final type of reaction is what's known as the net ionic equation. So in the net ionic equation, we are taking the total ionic and we're essentially just subtracting out anything that doesn't react. So in our total ionic equation, some species appear on both sides. These are what we call spectator ions because they're not actually doing anything. They're sitting back and watching the chemistry happen, just like a spectator at a sporting event. They're not actually involved in the chemistry. They're not undergoing any chemical change. So to write a net ionic equation, we take the total ionic and we remove the spectators. See if we can clean this up a little bit. So if we take a closer look at the total ionic that we wrote a minute ago, we can see that we have 2 sodium ions on the left and 2 sodium ions on the right. And we have 2 nitrate ions on the left and 2 nitrate ions on the right. So those things were sitting there in aqueous solution before the reaction, and they were sitting there in aqueous solution after the reaction. They didn't undergo any change. So sodium and nitrate are our spectator ions. So Na plus and NO3 minus are our spectators. So to write our net ionic equation, all we need to do is get rid of those and write out what is left. So we have 2Cl minus, lead 2 plus, react to form PbCl2. So that is our net ionic equation. So the benefit of the net ionic equation is that it's short and sweet, and that it focuses directly on the actual chemical change that's happening, that there's no extraneous information. And there really aren't a lot of drawbacks to a net ionic. The vast majority of the time, what your spectator ions are doesn't matter at all. You would get exactly the same reaction whether I had sodium or potassium here. It makes no difference. Or nitrate or acetate, makes no difference. But there are some rare circumstances where having a certain spectator ion can make some kind of weird side reaction happen that you don't want. So in those cases, having that information missing can be a problem. If like something weird happens when you're doing your chemistry that you didn't expect, and you're like, but I did this reaction looking at a net ionic, you're like, but I did this. I combined lead and chloride. It might be a spectator ion problem. It could, in theory. So not knowing like what somebody else did to get a certain result might prevent you from being able to replicate it. But for the most part, net ionics are great. They're short and sweet. They focus right on what's happening. They depict accurately how those things exist, that the lead and the chloride are separate ions, and then they attach to one another. So we'll be writing a lot of net ionic equations as the semester progresses in this unit and beyond, but you should be comfortable with all 3 of these types and converting in between them as well.